Good afternoon. Welcome to the presentation on binary analysis, the, the decompilation. LLVM. I'm Yaroslav Alexandrov, and Leonard Safi will help me. We will tell about the using this binary analysis compilation using the different languages and how we ended up there. We are a small team of developers from Moscow focusing on some certain types of solutions and backwards engineering. We're doing that for about 10 years. And we'd like to share some of our developments with you over the next 20 minutes or so. Right now we are working on a statistical analyzer for programs written with C and C++. And the main solutions that we want to see in our analyzer are listed here on the screen. First of all, the analyzer must support popular statistical analysis methods, such as template-based search for vulnerabilities and different types of data flow analysis, like taint analysis and more complex things for more sophisticated diagnosis. The analyzer must also have a scalable database, because the database is the heart of the analyzer. So without a big and expandable database, it will be of little use. Also, as one of the key features of the analyzer is Python API for scripting, because the main functionality of the analyzer is put outside to use this functionality in scripts, so that a group of analysts will be able to write new rules without trouble and without pain. And I, as a designer, as a developer, can focus on developing the engine of the analyzer. This is more or less how it happens. So, with some reservations, this arrangement is true for most of the statistical checkers that you can find on the market. So at the entry you have the CMTC language program, and then we have some kind of software model that is then uses predetermined rules and scripts. As you may have guessed, we use the LLVM library. We already had and still are having experience working with this library. This is why we decided it's good for this kind of task. A few words about LLVM. It is positioned as a set of technologies to develop compilation utilities. It includes a powerful language with a liberal license. So based on the LLVM, there are many popular front ends which are built on top with that. CSS Plus Objective-C Clam is one of them. Also, as an example, there's a compiler that uses Go and Rust. And by the way, congratulations with the Rust release. This was long awaited. In this way, using one of the existing front ends, we can have some ready-made internal representation. And because such analysis will be based on this LLVM, we can use as a front end any compiler that will give you a program model in LVM terms. For example, you can take Microsoft ULAC and with some reservations almost immediately have a C-sharp language analyzer. Still, as you analyze some programs, you find that they are linked or information systems use components or programs without the source code, such as libraries or executable files, especially a window platform. Apart from that, it could be legacy components with a lost source code or a modified malware of a binary type. In order to process such cases, we came up with this idea to use decompilation method to build internal representation of LLVM for subsequent analysis. Essentially, with this approach, the arrangement will not change much. There's only one new front end that translates the binary code. The main problems that you will face when doing the compilation, one of the problems that you face in doing compilation is a lot of loss of data. So when if it was not done properly at the programming level, you may lose programs, subprograms, variables, and classes of data and links. CP+ does not formalize the code. Depending on the compiler you use or the way you tune the environment, the result will be different. If you do the programming for Android, you can know that it is 1 byte. For Windows, 2 bytes. For Linux, it's 4 bytes. It's just one example, very simple. And also, your binary file can be packed. So, taking all these problems, we try to come up with ideas that are very desirable at the compiler level. Like with any LLVM front end, we want compilation to be done automatically. Another option would be interactive interaction with the user, but this is not priority for now. Another distinctive feature of the compiler is to be able to generate the maximum quality of output. I'll explain why it is important. There are some decisions already existing to translate binary files into LLVM, but unlike our solution, those translators do the translation from the source program into some microcode written in LLVM terms. So the purpose of such translators is so-called binary translation. We tried that approach. We had one project that where we implemented something similar, and the outcome was that we do need a high level of analysis, high level of substantiality. So we Our requirement for the decompiler is as much as possible to restore the source programs and subprograms, and as well as data types and variables. So essentially what we are looking for is an output which can be comparable to those of front ends of LLVM, or clanks in other terms. We also realized the support of high-level structures of CC plus language, information on polymorph classes, and exception handlings. Similar to statistical analyzers, the decompiler supports extendable database and tries to unpack a packed binary file if needed. Now we'll go through the operation of the decompiler, at least as it is implemented in our case. At the first phase, we restore the CFG programs, trying to isolate the data. We use the algorithm. It's algorithms that are typical of the compiler based on the platform. We use signature search, like a flirt, and do some other steps. After restoring CFG programs and all the other steps, things are better. We launch analysis of the data flow based on the representation that we get, and after that we have the source programs and variables restored. We are looking for global variables everywhere, that in all the places that were recognized as data. Based on the restored variables, we launch the process of restoring data types. So each instruction puts some limitation on the types of memory objects that will be used, so we can use some set of equations and then solve them. And so if the memory area can be both a pointer and a value, you use the pointer. The process of the compilation restores both structural and basic types. Most importantly, all local areas are restored, but we may come to that later. At the last stage, based on the presentation resulting from that, we generate LLVM, and the resulting LLVM is simplified for better readability. Particularly, we delete the dead code, and if possible, we move the memory objects into the register. Also, based on the AR that results from that, we can distinguish between functions and CFG regions. There's cycles and candle condition and others.
It's hard to see what's written in the code. I'll try to spell it out. It's hard to see what's written in the code. I'll try to spell it out. Can you see it, guys? Great. Looks like you can. So, as an example, I would like to show you a small piece of software. It's on the left. It's a simple one overall. There's a mine function. There's local buff massive. And if AC equals 2, the buff with the strcpy will record the argument argv1. After that, it will get the print function. So obviously the initial software contains 2 defects. This is the strcpy call with the user supply, and the printf call. Also in the form of the line, we use user-supplied data. On the right, you can see, if you see the image that we got, it's a result of decompilation. As a comparison, I show you. I wanted to show you the Clang generation of the same piece of software. So the one on the right, so both of them are quite similar and can be compared in quality. Of course, we lost the titles of the variables, though. So the bitcode that we got, we analyze with our statistic analyzer. And for the Clang, we get the similar results and find the range of vulnerabilities. Here's the example of how this is supposed to be working. We get to the entry base block. And see the argue argument. And we have the chain of users. We get to the call of strcpy, same way. Same thing with the local buffer. And the statistical analyzer will work on the call and we will find the vulnerabilities, such as the refill of the buffer, for example, the overfill of the buffer. A few technical details, try to be quick. So the architectures that are supported are now IPv6, XV6 in work. We support the three most popular images, and the knowledge base includes the stored standard libraries. An NPI of the popular operating systems. So the possible ways to use the decompilers in addition to statistic analysis is, for example, binary transmission. For example, the thing that I just showed you, based on the example that I just showed you and compiled for ARM Android. After that, I launched it on my tablet. It works just because the software is correct. You can also transmit the JavaScript with the help of a two-line scripture. Of course, generally, that's not always possible, but this is the point that is there. And this can be used in the work to generate these kind of algorithms. We also can use our tools for classic decompilation, for example. Essentially, we need to write another backend that will, for LLVM, that will display the pseudocode, and of course the graphic display of the software you saw it. Sometimes it's easier to use, it's more convenient to use it instead of some core. Of course, not always decompilation can be built correctly, can be done correctly. So, mostly, when we transmit, there are some inconsistencies and errors, or the software can just not execute a part of the code, or not identify the part of the code as code. However, during the analysis of binary vulnerabilities, often it's quite enough to support the partial transmission of the initial image, and essentially we were able to transmit the part of the software which contained the defect. We did it with a sufficient quality, and we found the piece of the code with vulnerability, so it's a win. So that's why we support both partial analysis and partial transmission of the code. In addition, we have the database and signatures of the vulnerable components of the software, which are used to search for vulnerabilities just by signature of the components. This is it. Thank you very much. If you are interested in decompilation, please pay attention to the links below at the right. We have recently published the source code of our other decompiler, so it's open, it's available. Thank you for listening. Sorry, I cannot hear the question, so I hard to translate it. The question is the following. At this image, on the left, this is the LLVM, and to the right, it's your generation, right? So do you understand that on the left, you got this export, which was on the source code, and the right on the binary? Yeah, on the binary. Yes, exactly. Thank you very much. Two questions. First of all, does the Python IP supports the modification, the change of the LLVM modification, or it's only static analysis? So far, only statistic analysis, but the LLVM has Python bidding, and nothing stops you from changing that LLVM right there. Another question: do you plan to, or is there perhaps the possibility to decompile object file which are generated by GCC or Visual Studio, and the analysis of those things? So is it possible? Are you going to introduce that? Yeah, we've been thinking about it, and we're going to build that in because we need for some other objectives. Generally, there is no significant difference here between this thing and the transition of the binary that we have now. Any more questions? Are there? So we talk about statistic analysis. This is a ready product, or it's still a work in progress. For the static analysis, is there a separate static analyzer that works without decompiling? Yes, we have the analyzer which works in bitcode, LLVM bitcode. So it's a commercial product that can be bought and used, or it's still in development. It's still in development, and I believe we will, of course, let you know when it will be available. So can I ask you for a demo version? No, it's too soon for that. Do I understand correctly that it's a GPL license? Yes, it's a GPL license on GitHub, GPL 3 license exactly. Are you planning to change it for something? Not yet, not so far. Thank you very much.